This is an answer key for molecular model building. The bulk of this work is going to be determining the Lewis structure for each of these substances. To do a Lewis structure, we need to start by counting valence electrons in each of these items. We count the valence electrons by finding the atom on the periodic table and the group number that that atom happens to exist in. So nitrogen's in 5, V, fluorine's in VII, which is 7. There's one copy of nitrogen, so that's 5 electrons plus 7 times 3, so it's 21, and 5 is 26. Then we need to determine our central atom. When we have nitrogen and fluorine together, we're going to do the most electropositive, the one that's furthest away from fluorine. And nitrogen's further away, and fluorine is itself, so we don't want that one. Additionally, there's only one copy of nitrogen. The one copy atom is off in the central atom. 3 copies of fluorine. Next step is to connect the remaining atoms to the central atom using a single bond. After that, we want to follow the octet and duet rules. We don't have hydrogen, so we only have to worry about octet rule. We need to give each atom 8. Start on your peripheral atoms. So here's 4, 6, 8. That's used up a total of 2, 4, 6, 8, 10, 12 electrons. 14, 16, 18, 20, 22, 24. You still have 2 left over electrons, which is good because nitrogen needs to have 8 as well. Double check your work, make sure all atoms have octets, and we've used only 26 total electrons. Your picture can have no more or no less than this. 2468, 2468, 2468, 2468, and we have 26. As far as the model goes, we need to find a atom in our model kit that happens to have 4 holes. I know that there's 4 holes because there's 4 pairs of electrons attached to a central atom. When we say pairs, we're going to talk about lone pairs or bonded pairs, the lines. Doesn't matter if they're lone or bonded, you need that number of holes. So we need 4 holes, and the black model spheres have 4 holes. Then I need 3 fluorines. It doesn't matter as long as they're the same color for our class what to choose. And then since these are single bonds, we'll just choose the rigid. We will choose the rigid. We will choose the, we will choose the rigid bonds. So this is what our model looks like. You can see it's 3-dimensional structure. In class, you're going to take a picture of this with your Chromebook and insert it into this square using the file menu insert, then the picture, insert image, and then take snapshot. The overall geometry, we can either look at this model or we can look at the structure itself. We're going to be using A's, B's, and E's. So we have a central atom, that's A. We're going to count how many types of bonds or how many bonds we have attached to that atom. We have a single, a single, a single, so B sub 3, because there's 3 single bonds. Then we have 1 lone pair of electrons right here. You can see that also in our Lewis structure, so that means E. We can use this code and look up that atom, or that geometry on our green resource sheet. AB3E right here is called trigonal pyramidal. Now, to determine polarity, we're going to look at our central atom and ask ourselves, is the central atom 100% surrounded by the exact same thing? So I have fluorine, 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 lone pair. That's not 100% surrounded, which means this will be polar. And if you look at the actual model, it's pretty clear that you have a side that has atoms, the white atoms, and then you have a side that doesn't have atoms. You can see two distinct regions on this model. Resonance, to even possibly have resonance, there has to be a double or a triple bond. This does not have a double or triple, so this is null. Next model, sulfur is a group 6, chlorine is a group 7. There's 2 copies of chlorine. 7 times 2 gives us 14, plus 6 more gives us 20. Central atom. Between sulfur and chlorine, sulfur is further away, there's only 1 copy. Attach your remaining atoms using single bonds. Give each of your remaining atoms an octet. So we've used 2, 4. That means 20 minus 4 is 16. So we have 16 dots to go. There's an octet for chlorine. We've used 2, 4, 6, 8, 10, 12, 14, 16. Both chlorines have an octet. 18, 20. So that's our picture. If we look at our central atom, we need to find a sphere that has 1, 2, 3, 4 holes in it because it has 4 pairs of electrons. And then we need to have 2 bonds. So that looks like so. Again, take a picture, insert it into that space. For the overall geometry, we have A for atom. There's 1 bond, 2 bonds. 1, 2. So A, B, sub 2. 1 pair, 2 pairs. 2 pairs of electrons. A, B2, E2. We can look that up on our green sheet. A, B2, E2 is called bent. If you look at the model, you can clearly see there's one side that has atoms, one side that doesn't, so this is polar. Looking at the Lewis structure, not 100% surrounded by the exact same thing, so this is going to be polar. No double or triple bonds, so resonance here is no. Carbonate ion. Carbon lives in group 4, oxygen is in group 6, there's 3 copies. And then since we have -2, that means we have 2 extra electrons. We have additional 2 negative charges, which can only come from electrons. 6 times 3 is 18, plus 2 is 20, plus 4 is 24. Central atom. If you have carbon, put it in the middle. There's also only 1 copy of carbon. Attach the rest of your atoms with single bonds. So we've used 6 electrons. 6 electrons from the 24 means I have 18 left. And I can tell if I have 1, 2, 3 atoms, 18 divided by 3 is 6 electrons each, which is good for the oxygens because each oxygen would have an octet, but that means we're going to be short for the carbon. So if we just work our way here, 2, 4, 6 around that oxygen, there's 12 left, 2, 4, 6 around this carbon, that means there's 6 left, 2, 4, 6. So I've used up all 24 electrons, but carbon doesn't have an octet, so we have a problem. What we need to do is we need to make our electrons more efficient by sharing them, and we're going to take this lone pair, or we could take this lone pair, or we could take this lone pair, it doesn't matter, off of any of these 3 oxygens, and we're going to make it into a double bond. So I'm basically taking these 2 electrons and slide them right here, but at the same time, that means I need to erase the ones that were the lone pair. They've become a shared pair to make those more efficient. And this right here is why we use pencil when we do the model building. If you look at this picture, then the whole thing has a charge on it, so we're going to write it like that. My central atom still has 2, 4, 6, 8 electrons. In other words, 4 pairs of electrons, which means that I need to have a 4-hole central atom. And that can come from a black sphere again. And then typically the red spheres are used for oxygen. So I have to use a double bond this time, which requires the flexible bonds in the bond kit, just like that. And then two rigid single bonds, which will look something like this. We're making this molecule. So you take the picture, insert it into that box. Looking at this picture, or looking at the Lewis structure, we have one bond, two bonds, three bonds, a single, double. So we have a central atom, B, three bonds. If you look AB3 up on your resource, AB3 is right here, is called trigonal planar. And try, 1, 2, 3, it's all on the same plane. All of these reds are all on the same plane. They're flat. This central atom is completely surrounded by oxygen. There's only oxygen, which means that this will be a nonpolar substance. Resonance. Is there a double bond? Sure. And this double bond could have just as easily been on this oxygen or this oxygen. So call this oxygen A and B and C. The double bond could have moved anywhere, so that can resonate. It can bounce around between those three locations. That means an accurate picture would be this, and it would be this, and it would be this. Three ways we can draw that picture. The ammonium ion has 5 electrons for nitrogen. Hydrogen is in group 1. There's 4 copies. If you're +1, that means you lost a negative charge, so we have to subtract an electron. 1 times 4 plus 5 is 9. Subtract 1 makes 8 valence electrons. Central atom, never put hydrogen there. We only have 1 copy of hydrogen or nitrogen. Attach the remaining atoms. We've used 2, 4, 6, 8. We only have 8. Nitrogen has an octet, and then luckily hydrogen only needs a duet. So we have 4 different pairs of electrons stuck onto our central nitrogen atom. So I need a atom with 4 holes, and the black sphere has 4 holes. And then the 4 rigid single bonds, this is the molecule that we just made. So we have an atom, bond, 1, 2, 3, 4, so AB sub 4. If you look up AB sub 4, AB sub 4 is called tetrahedral. As far as polarity, nitrogen's 100% surrounded by the hydrogens, so it's nonpolar. Every side looks the same, no double or triple bonds, so no way that there could be a resonance. Flipping to the second page of this lab, HCN, hydrogen is in group 1, carbon's in group 4, nitrogen's in group 5, for a total of 10 valence electrons. Central atom, if carbon's there, put it in the middle. Attach your other 2 to carbon. Now, hydrogen's already set with a duet. It only needs that shared pair. Carbon and nitrogen both need octets. We've already used 4 of our electrons. We only have 6 left. 10 minus 4 is 6. So we can divide them evenly, 3 and 3, which means that we're going to come up short, which means we're going to for sure need a double bond. Make your peripheral atoms happy first. So we have 2, 4, 6, 8, 10. We ran out. Carbon only has 4, so it needs 2 more, which means we need to move this lone pair, attach it between carbon and nitrogen, This lone pair, same thing. They're going to both get moved, which means we have to form a triple bond. And erase those lone pairs because they just became shared pairs between nitrogen and carbon. As far as this molecule is concerned, we still have a total of 80 electrons, or 4 pairs, which means we need to have a 4-hold atom. So again, we keep going back to the black sphere. And then we're going to need a triple bond, so you'll need 3 of the flexible pieces and then 1 of the rigid pieces to make a triple bond. And the molecule that you come up with looks something like this. Figuring out A's, B's, and E's, we have our central atom carbon. For bonds, I see a triple bond, I see a single bond, which means AB2, no lone pairs on that central atom. AB2 on the green resource sheet, AB2 is called linear. Now, polarity, carbon has hydrogen on one side, nitrogen on the other, which means that there's going to be some degree of polarity to this. This one does have a triple bond, but this triple bond can't move because hydrogen cannot have any more electrons. So even though there's a triple bond and there might be resonance, this one cannot have resonance. Selenium hexafluoride, so SeF6, Se has a group number of 6, plus fluorine has a group number of 7 times 6. 7 times 6 is 42, plus 6 more is 48. Selenium is going to be central because it's the single atom that's also further away from fluorine. Happens to live in row 4. Our rules say this, that after row 4 you can break the octet rule. So selenium is going to connect the 6 remaining fluorines with single bonds, and selenium is actually going to have 12 total electrons, but that's okay. You can use d sublevel electron orbitals to do that. Now, selenium is set, the fluorines each need more electrons. 48 minus the 12 that we've used gives us 36. There's 6 more fluorines, so 6 goes into 36 6 times, which is perfect, because each fluorine needs 6 more electrons. So giving each fluorine an octet, that's all the electrons that we need. To build this molecule, we need to have 6 holes, because there's 6 pairs of electrons stuck to that selenium. So most of the model kits have 1 or 2 atoms in there that happen to have 6 holes. They tend to be yellow. I do believe some of the model kits actually have a gold, a silver or a gray colored atom with 6. We're going to use single bonds, the rigid kind. And we will attach 6 fluorines. And again, we don't care about the color for our class. We just want to have them the same because they all represent the same. And this is the molecule that you end up with. As far as A's, B's, and E's, we have a central atom, selenium, bonds. 6 single bonds, so AB sub 6. AB sub 6 is called octahedral. As far as polarity is concerned, selenium is 100% surrounded by the fluorine, so no polarity, no doubles, so it's going to be no resonance as well. So nonpolar, no resonance. CH2O, carbon lives in group 4, hydrogen lives in group 1, 2 copies. Oxygen lives in group 6. 1 times 2 is 2, plus 6 is 8, plus 4 more is 12. Central atom, carbon if you have it. Connect the remaining atoms with single bonds to your central atom. We've used 2, 4, 6 electrons. There's 6 left. Hydrogen set. If I put all 6 on oxygen, oxygen will be set, but carbon will only have 2, 4, 6. So 2, 4, 6 electrons on oxygen. We have 2 left, which will be the pair that's right here, but we're going to move that to a double bond so that both carbon and oxygen are content, they're happy. We need to use a central atom that has 4 holes because carbon has 4 pairs of electrons attached to it right now. We'll need to use 2 flexible pieces and 2 rigid pieces because we need that double bond. And our molecule will look something like this. A's, B's, and E's, central atom, bonds, a double, 2 singles, no lone pairs. AB3, if you recall earlier, is called trigonal planar. And this is a triangle, and it's also flat. It's on the same plane. Polarity. Carbon has oxygen and it has hydrogen, so there's clearly a side that has yellow and a side that has white, which would make this polar. This does have a double bond, but that double bond can't move to these other locations, so it's no resonance. PBr5, phosphorus is a group 5, bromine's a group 7, there's 5 copies. 7 times 5 is 35, plus 5 more is 40. 1 copy of phosphorus, so that's our central atom. Connect the remaining atoms with a single bond. Now phosphorus has more than an octet, but that's okay because phosphorus is in group 3, or row 3, excuse me, so it can break the octet rule. We've used 10 electrons, that means 40 minus 10 is 30 left. We have 5 bromines, so each one can get 6 dots, which is perfect because that's what's needed for an octet. So there's our Lewis structure for PBr5. We'll need to find a atom that has 5 holes, and there's this kind of purplish one. It's going to look black on the video, but there's a purplish one in some of the kits that has 5 holes in it. We need 5 holes because there's 5 pairs of electrons stuck to the central phosphorus. All of them are shared bonded pairs. We have 5 rigid bonds because they're all single bonds. I'm just choosing white peripheral atoms. So this is the molecule that we get. As far as A's, B's, and E's go, A, B, there's 5 single bonds, no lone pairs. A, B, 5 is right here. It's called trigonal bipyramidal. Completely surrounded by the same thing, so there's no distinct sides. It's nonpolar, no double or triples, so no resonance. SO4, sulfur lives in 6, oxygen lives in 6, there's 4 copies, -2 means plus 2 more. 6 times 4 is 24, plus 6 is 30, so 32, sulfur central. Attach the remaining oxygens. If you use all 32 electrons, you get a picture that looks perfectly like this. Everyone has an octet, -2 charge. The atom, or excuse me, the molecule looks like this. It's got a central atom with 4 bonds, which calls tetrahedral. This is 100% surrounded by the same thing, so it's nonpolar. No resonance because there's no double or triples. Lastly, bromide ion has 7 valence electrons. Oxygen is in 6 times 3, plus 1 more. 18 plus 7 is 25, 1 more is 26. Central atom is bromines. The single is further away from fluorine. Give each atom an octet. There's 12, 14, 16, 18, 20, 22, 24. Last pair goes on bromine. Again, this is a charged particle, so it's like so. We need to have a 4-hole central atom. Your molecule looks like this. As far as A's, B's, and E's go, A, B, 3 single bonds, a lone pair of electrons. We haven't used that for a while. It's right here, or right here in your Lewis structure. If you look up AB3, it's called trigonopyramidal. Central atom's not 100% surrounded, so there's a distinct space where there's no atoms, and a distinct area where there are atoms, so that's polar, no doubles or triples, so that is a no resonance structure.